You must still be impressed by the screaming and stimuli of the turbo-based turbodrome in the funfair. So let me now interpret some basics of quantum mechanics of quantum jump in a much amusing form of a people jumping from a building. We take a guy as an electron who was lazy and tended to watch TV all day and night with a low energy staying at the ground, whose state we call ground state. One day there's an external interference of energy, which can be any form like friction, heating, etc. So the man was forced to climb the roof of building to an excited state. Here we're going to introduce the term of quantum jump with a radiation. When an electron is further away from the ground, which is a positive charged nucleus, it obtains a higher energy. As the electron comes downstairs, it emits only light energy by releasing photons. The color of the light, which is dependent on how much the energy level changes. If it has short high jump, it might emit a longer wavelength of light energy, such as red rays. By contrast, if the electron leaped with a greater energy level change from an excited state to a more stable state, it releases rays of shorter wavelengths. Here it can be a blue one. The scientists by using spectrometers to compare the spectra to justify the existence of orbitals in atoms. Atomic model. Look inside an atom. Nuclear number is equal to the number of protons plus the number of neutrons. Atoms are neutral. Ions are formed by gaining or losing electrons. Nucleus is far away tiny. If we compare an atom as a football pitch, a nucleus will be seen as merely a pea. The electrons are also small enough, therefore there are a lot of empty space in an atom. So when a charged beam is projected, only protons and electrons deflect. Neutron does not deflect. Nuclear number is equal to the atomic number. We use the symbol to represent an isotope. X is the element, Z is the proton number, A is the nuclear number. Relative atomic mass is the average mass of neutrally occurring atoms based on the scale of carbon-12 has exactly 12 units. The scientists use the mass spectrometer to measure and calculate the relative mass of an element by adding the product of isotopic mass times percentage abundance. For us, we just need to give three significant figures. Relative molecular mass is the same thing, but for compounds. Isotopes. Isotopes are the atoms which have the same proton numbers but different neutron number or atomic number. The naked proton is hydrogen, which is without neutron. By adding neutrons to hydrogen, we got deuterium and tritium. The isotopes of hydrogen are used in nuclear fusion, usually occurring on the sun, releasing solar energy. By contrast, isotope uranium-235 is used in nuclear fission to generate electricity in manufactories. Isotopes can be used to detect the leakage of underground pipes. Its feature of penetration can be used to measure and control the thickness of paper. It can also be used in medical treating or carbon dating by using carbon-14. Electrons in atom. Villa and Arena. Simple electronic structure. Here's the lithium configuration. Let's take a new look. Familiar with is the principal quantum shells, which are also called energy levels. We give the atom symbol as N. As principal quantum shells N increases, the attraction between positive nucleus and negative electrons decreases. The energy of electrons itself increases. The principal quantum shells are holding less tightly. Evidence of electronic structure. Here, we introduce a new term, ionization energy. As we know, ionization is a loss of electrons. Therefore, ionization energy is an energy used to remove one more of electrons from one more of atoms of an element in a gaseous state to from one more of gaseous ions. The formula is at the bottom. Successive ionization energy. First, ionization energy of successive elements. The energy for removing the outermost electrons, which need a force. The first depends on three main factors. The first one is a charge on nucleus, which is positively related to the attraction. The second one is the distance of outer shell electrons from the nucleus, which is inversely related to the attraction force. There's also a shielding effect, which refers to the electrons between the outer electrons and the nucleus. Interpreting successive ionization energy. Comparing the ionization energy of hydrogen and helium. The increase in ionization energy is mainly due to an increasing nuclear charge. Comparing the ionization energy of helium and lithium. With the increasing of positive nuclear charge, the distance enlarged, which creates a shield at the same time, leading to a drastic fall in IE. Comparing the IE of lithium and beryllium. Nuclear charge increasing is dominated as well. Comparing the IE of beryllium and boron. Because of the existence of a subshell, p-subshell, consisting of three orbitals px, py, and pz, the distance between nucleus and the electrons is increasing. According to the Pauli exclusive principle, there are only two electrons in one orbital. Therefore, an inter-electron repulsion means 2n4 and overall force holding the electron to the nucleus. So, the energy required to remove an electron falls. Between the nitrogen and oxygen, we can see a reduce in IE, contributing to another spinning pair repulsion. At the junction of the second period and third period, a rapid fall in IE emerged between neon and sodium. The increase in distance and shielding effect overweigh the factor of growing charge. The attraction decreases. However, across a period from lithium to neon, there is a general increase in IE. Although the distance and shielding effect are constant, but the increase in positive charge on nucleus brought to it. Here, let's take a look at subshells and atomic orbitals. The shells may be divided into subshells known as S, P, D, and F subshells, consisting of 1, 3, 5, and 7 orbitals, respectively. S orbital is spherical. Each orbital can hold a maximum of 2 electrons, so it's holding a maximum of 2 electrons. 3 orbitals in P subshell are lobes-like or in dumbbell shape along X, Y, Z axis. They are holding a total maximum of 6 electrons. 5 orbitals in this subshell are in a complex shape. They are holding a total maximum of 10 electrons. F subshell consists of 7 orbitals with a much more complex shape. They are holding a total maximum of 14 electrons. Electronic configuration. This is an electron configuration of hydrogen. The first number stands for the quantum number, or principal energy level. The next letter represents the subshell. The number on the right top corner represents the number of electrons in the subshell. Shorthand. The symbol of argon with brackets represents the noble gas core, briefly narrated the first 18 electrons. Here's an example of potassium. Electronic configuration of ions. The outer shell electrons are lost first. We noted the D-box elements here, whose 4s electrons are lost first, because the 4s electrons are in the outer subshell. Let's take a look at 3 principles for the configuration. The first one is Aufbau principle. Aufbau is a German word, means build-up or construction. It indicates to fill the lowest energy level first. For example, 1s has to be before 2s. The second one is Pauli exclusive principle, referring electrons spinning in opposite directions. The boxes on the graph are orbitals. The arrows indicate the spinning electrons. The opposite directions refers to the repulsions. One is Hahne's rule of maximum multiplicity. When 2 electrons in one orbital, electrons repel each other. So we fill the box first singly, then doubly. Let's take a look at 3 principles for the configuration. The first one is Aufbau principle. Aufbau is a German. Let's take a look at the tendency from boron to oxygen. Following Aufbau principle, electrons fill the lowest shell first, from 1 to 2. Every subshell must be full before the electrons begin to fill the next shell. The electrons fill the subshells in order of S, P, D, F, except the subshell 4s, which is filled before 3d. When electrons fill the subshells, they first fill each orbital singly before pairing up. During these procedures, pay attention to using opposite-facing arrows to demonstrate their opposite-facing spin. Generally, the relative energies of subshells are increasing from S to F within a given energy level. However, apparently their energy level overlaps. For example, 4s electrons fill up first, then 3d electrons. No matter how, there are always exceptions deferring to other rules, such as chlorine and copper. There are extra stability of half-full or full sets of d orbitals before fully occupied 4s orbitals. Orbitals and periodic table. Let's take a look at the periodic table. We separate it into basically 4 blocks. Group 1, 2, including hydrogen and helium, are in the s block, referring to the s orbital which is in the outer subshell. Groups 13 to 18 are in the p block. The transition metals are in the b block, and we put ethanides and lanthanides in f blocks. The position of an element within the periodic table can be used to identify its electronic configuration. Elements are placed in rows corresponding to the shell in which their outer electrons are contained. Electrons are placed in blocks dependent on the subshell in which their outer electrons are contained. Nitrogen is in the second row and in p block, so its outer electron shell is 2p. It's the third element in the row in p block, so it's 2p3. Its electronic configuration is 1s2, 2s2, 2p3.